For second part of the chapter 21, we are going to look at more reactions of acid derivative. One common reactions for all acid derivative is the nucleophilic acyl substitution. So the acyl group is the R-CO double bond. So this is the acyl. And in this position, when we have a nucleophilic substitution, we can change the functional group. We can go from interchange between the acid derivatives. We can go to carboxylic acid to esters, to amide, to acid chlorides, and all. So basically, a nucleophile is going to come in and leaving group would leave. The carbon cannot have more than 4 bonds. So when nucleophile comes in, the weakest bond will break over the oxygen, would give the negative charge to oxygen. So you do have like a tetrahedral intermediate. It's not stable. So the pair of electron would go back, leaving group is going to leave. That's basically the general mechanism for all nucleophilic acyl substitution of the acid derivative. When is the substitution reaction, the better the leaving group is, the more reactive the substrate is, the faster the reaction is going to be. So if you look at the trend in the reactivity of the acid derivative, you see that acid chloride is the most reactive, and the major reason for that is Cl is a good leaving group, or it's the best leaving group among other, the blue color, all of those are the leaving group. So Cl chloride is the best leaving group, and the carboxylate ion is the second. Then we have the alkoxide and then the amide. So amide is going to be the least reactive, but chloride is going to be the most reactive acid derivative. So we have your carboxylate. This is going to be the least reactive, and it is going to be the most stable one. So all these reactions, like between the acid derivatives, they are interchangeable. One can be converted to the other one, and they are all kind of connected. But if you hydrolyze any of the acid derivatives, you can go to carboxylic acid by the hydrolysis. So this diagram shows the interconversion of the acid derivative, and after the most reactive can be converted to least reactive, like spontaneously. So acid chloride can be converted to any of the other acid derivatives, to acid anhydride, to ester, to amide, and to carboxylate ion by hydrolysis. But carboxylate or carboxylic acid to acid chloride, it's not spontaneous, because acid chloride is more reactive than the carboxylate ion. Acid chloride to anhydride. So basically you have your leaving group, which is the Cl. So you need your nucleophile, and the carboxylic acid would act as the nucleophile. In this case, the general trend that I did mention in chapter 20, and I said is not the mechanism, is not the rule, but it's just a general trend. Hydrogen from nucleophile with the leaving group. So hydrogen from nucleophile with the leaving group, or one hydrogen from nucleophile with leaving group, would give the byproduct of HCl. And then the rest of the nucleophile is going to form bond with the carbonyl group. This is like overall reaction, since it works for all interconversion of acid derivatives. So I can say it does work, and is going to make your job easier. So a hydrogen from the nucleophile with the leaving group would give the byproduct, the rest of the molecule from the nucleophile is going to form bond with the carbonyl group, and it gives you the product. So in order to form acid anhydride, you're in the lab, you're going to use acid chloride plus carboxylic acid. This is not a good method for industry because acid chloride is very expensive, or more expensive than the acid anhydride. So it's not going to be a good method for industry for bulk, but for the lab is a good method to use. Acid chloride to ester, if you remember, formation of ester was any acid derivative plus alcohol would give you ester. And so if we follow the same trend that we had, a hydrogen from the nucleophile, so alcohol is nucleophile, is not the best nucleophile, is a weak nucleophile, that's, but the leaving group is a good leaving group. So you have weak nucleophile, but good leaving group in this case. You don't need the acid, you don't need to use the acid catalyzed reaction. So hydrogen from the nucleophile with the leaving group would give the byproduct. The rest of the molecule is going to form bond with the carbonyl group, and it gives you ester. Basically, any acid derivative plus alcohol, it gives us ester. Acid chloride to amide. With the amide is going to be the same. Any acid derivative plus ammonia would give you primary amide. Any acid derivative, like this is a secondary amine. Amine, if you look at NH3, okay, that's ammonia. And if you take like a CH3 replaced with one of the hydrogen, and you have two hydrogen attached, this is the primary amine. Okay, a secondary amine would look like this. You have CH3, and then hydrogen. So based on number of hydrogens, you can count. If it's NH2 is primary, if it's NH is secondary, if there is no NH and you have like a tree of the carbon attached to it, is going to be tertiary. Basically, you're counting carbon-nitrogen bond. Okay. If it's a secondary amine, in this case, it will give you tertiary amide. So this amide, if there are two carbons, is going to be tertiary amide. Anhydride to ester is another acid derivative. Okay, you have your acid derivative. So the leaving group is acetate leaving group, and you have carboxylate, sorry, in general, carboxylate leaving group, and your nucleophile is alcohol. A hydrogen from nucleophile with the leaving group would give you byproduct, basically is this byproduct. And then the rest of the molecule of the nucleophile with the carbonyl group is going to form bond, and it gives you ester as a product. So alcohol attacks to one of the carbonyl group of the anhydride, forming this tetrahedral intermediate, and then the electrons would go back and drop in, leaving group would leave. That's the mechanism. But when I was talking about the general trend, I already said that that's not the mechanism, but it's the general trend, and it does work. Anhydride to amides. So anhydride to amides, you have to bring ammonia or amine. If you bring ammonia, you would get primary amide. If you bring primary amine, you get secondary amide. And if you bring secondary amine, you would get tertiary amide. So ammonia would yield primary amide. Primary amine would yield secondary, and secondary amine would yield tertiary amide. If we are looking for the trend, hydrogen from this nucleophile is going to react with or combine with the leaving group, and it gives a byproduct. Because this is anhydride, basically provides two molecules of the acyl group, and then the rest of the molecule is going to form bond with the carbonyl group, and it gives you the amide. So you get amide plus carboxylic acid. Ester to amide. For ester to amide, if it's a primary amine, you would get secondary amide. Amine is acting as a nucleophile. OR is the leaving group, this case. So one of the hydrogens from the amine group with the OR would give you the byproduct of alcohol, and then the rest of the molecule form bond with the CO double bond, and it gives you amide. So the nucleophile that you're using, it should be a primary amine or ammonia. Okay, heating is required because you don't have the best leaving group and you don't have the best nucleophile. So you have the leaving group leaving, and then the nucleophile is going to attach to the CO double bond. What is trans-esterification? In trans-esterification, you start with an ester, you add alcohol. Large excess of this alcohol is going to replace the OR group. So you basically change the alkyl, the size of the alkyl group. So if you want to change the ethyl group with methyl group, you start with the ethyl benzoate or the ester that you want to replace the alkyl group with the methanol. So you have to use excess amount of the methanol. So in order for the methanol to be used, it's going to replace the ethyl group, or the ethanol is going to form as a byproduct, and you get methyl benzoate rather than the ethyl benzoate. So for the general trend, don't know how many of you actually like this trend. Hydrogen from the alcohol with the leaving group would give you the byproduct. So you have the ethanol as a byproduct, and then the rest of the molecule would combine with the CO double bond. Hydrolysis of acid chloride and acid anhydride is going to basically, when you hydrolyze a carbonyl group, the bond between carbonyl group and the leaving group is going to break, and you're adding water. So when you break this bond, you're adding water. Basically, you're adding H and OH. So H is a plus, OH is a minus. And if you break this bond, then chloride is going to be minus, and this carbonyl is going to be plus. H is going to form bond with the negative side, and OH will form bond with the positive side. So you get carboxylic acid plus HCl. For esters, again, just think about adding H and OH unless you're looking for the mechanism for the reaction, okay? So H will add to oxygen. So this bond will break carbonyl group and the leaving group. The bond between carbonyl group and leaving group would break. H will add to the oxygen, and OH will add to the carbon in this case. So you would get the carboxylic acid plus alcohol. If it's in a basic solution, if it's a base catalyzed in a basic solution, your carboxylic acid is going to be deprotonated, and you have carboxylate ion. This is because you're dealing with the basic solution. If it's acidic solution, then this is going to be protonated, and you have carboxylic acid plus alcohol as the product. Saponification is basically the hydrolysis in the fatty acid, which are esters. They have ester functional group. Hydrolysis of ester in a basic solution is going to remove or break out the bond between the fatty acid and the ester functional group is going to basically be hydrolyzed. The CO single bond is going to break, and to each one you're going to add the OH and then H. And because this is in a basic solution, when you do base catalyzed, it's going to be deprotonated. So you have O minus here. And since you have sodium, is going to be the sodium salt of the acid. And sodium salt of the acid is, sodium salt of the fatty acid is soap. Hydrolysis of amides. What would you get as a result of hydrolysis of amide? You are going to get carboxylic acid, because that's one of the definitions for acid derivative. If amide is acid derivative, is going to give you carboxylic acid when you hydrolyze it. Plus amine or ammonia, and if you have a primary amide, it would give you ammonia. If it's a secondary amide, it would give you primary amine plus the carboxylic acid. So basically, it's a reverse reaction of what you had before. Okay. So if you look at the final product, we have the carboxylate. And this is, again, because it's a basic solution. Under acidic solution, it would have been carboxylic acid plus the ammonia. But in basic solution, the acid is going to be deprotonated. So in a basic solution, the hydroxide is going to attack the carbonyl group. As a nucleophile, is going to attack, the pi bond breaks over the oxygen. Then the the carbon now, the pi bond is going to come back, the pair of electron would come back, and elimination would happen, or the leaving group is going to leave. And the leaving group, in this case, because it's a basic solution, it doesn't get the hydrogen from the acid, but it gets the hydrogen from the deprotonation of the carboxylic acid. In the acid hydrolysis, basically, hydrogen is going to come in first. Hydrogen, when hydrogen comes in, is going to protonate the CO double bond. Then the water is going to act as the nucleophile. Now that this carbonyl group has been activated, then water as a weak nucleophile can act or can react, and then the pi bond breaks, because the pi bond is going to break over the oxygen. Carbon cannot have more than 4 bonds. The pi bond breaks over the oxygen, and now we have the H2O taking over the plus charge. That H2O with the plus charge is going to be very unstable. Then, as we have seen in the past, the hydrogen stake is going to be removed with the plus charge to leave the OH back. So when you have the OH back, now you get the you have the the diol. So the ammonia NH2, because it's kind of a strong base, is not going to leave on its own, is not a good leaving group. But when you protonate it, it would change to NH3. NH3 is a weaker base and it would leave. It's a better leaving group than the NH2, definitely. It's going to leave. And when it leaves, is not taking the plus charge. So the plus charge goes back to this molecule. And the only way that you can remove the plus charge is going to be with the hydrogen. So you remove H plus. And when you remove the H plus, then you're going to get the regeneration of the CO double bond. So you have the NH4 plus, and this is in the acidic solution. What happens in acidic solution? The carboxylate is going to be protonated. So you basically have a carboxylic acid, and ammonia is going to be also protonated, and it changes to NH4 plus to ammonium ion. In acidic solution, however, you can have NH3 and carboxylate ion. The acid is going to be deprotonated. Hydrolysis of nitriles, if you remember, once I said if you have a CN double bond, which is imine, and you hydrolyze it, it's going to change to CO double bond. But if you have CN triple bond, you hydrolyze this, it's going to change to COOH. So hydrolysis of nitrile would give you carboxylate ion or carboxylic acid. In acidic solution, you will get carboxylic acid. In a basic solution or base catalyzed hydrolysis, you always get carboxylate ion, because in basic solution, acid will be deprotonated. In acidic solution, NH3 is going to be protonated, and you have NH4 plus change to ammonium ion. Next type of reactions of the acid derivative is reduction. Reduction meaning adding hydrogens. So one general trend, it's going to help you. Reduction of all acid and acid derivative would give you primary alcohol, except the ones that they have nitrogen, they contain nitrogen. If it contains nitrogen, it would give you amine. If it doesn't have nitrogen, it will give you primary alcohol. So reduction of ester with LAH would give you primary alcohol. Okay, that's an ester with the LAH would give you primary alcohol. That's the major part. The carboxylate acid is going to be the change to primary alcohol. The leaving group, which is alkoxide, also would be protonated, and it gives like byproduct of the smaller molecule of alcohol. So reduces the ester to primary alcohols. When you say lithium aluminum hydride, basically it contains hydride ion, and hydride ion acts as a strong nucleophile. And this nucleophile can attack the carbon from the carbonyl group. The pi bond breaks over the oxygen, changes to alkoxide, and then it can be protonated. Or first is going to change to aldehyde, and then from aldehyde we change to primary alcohol. So it's a two-step reduction, basically. That's why you need the LAH as a strong reducing agent. From carboxylic acid to primary alcohol, you need a strong reducing agent. If you want to reduce it to aldehyde, so if you want to reduce it to aldehyde, which is one-step reduction, you cannot use LAH, which is a strong reducing agent. LAH is lithium aluminum hydride with the 4 hydrogen in form of the hydride. But when you have when you want to poison this, or if you want to stop in the aldehyde position and do not continue with the reduction to primary alcohol, you have to poison it. And in order to poison it, you are going to take 3 of this hydrogen, and instead of the 3 hydrogen, you are going to use 3 T-butoxide as the bulky base, replacing a bulky alkoxide, replacing this hydride, 3 of the hydride ions. You only have 1 hydride, okay? When you have only 1 hydride, so you do have 1 hydride in the lithium aluminum hydride, and the other 3 are replaced by alkoxide or bulky alkoxide. Now, this is going to act as a mild reducing agent. And if it's a mild reducing agent, as soon as you get to the aldehyde, will stop at the aldehyde. It's not going to go to primary alcohol. Well, we learned about sodium borohydride also, and says sodium borohydride is a weak reducing agent. But when it comes to acid derivative like acid chloride, you cannot use sodium borohydride. Sodium borohydride would only work on aldehydes and ketones. So you can't use sodium borohydride. You have to use LAH, or you would use poison LAH. If you use LAH, it will go all the way to primary alcohol. If you use poisoned LAH, it will stop at the aldehyde. Now, other reductions, if you have, remember I said, if your acid derivative contains nitrogen, it will go to amine. So if we have a primary amide, it would change to primary amine. If you have a secondary amide, it would change to secondary amine. Tertiary amide would change to tertiary amine. Because when you do reduction, you're basically removing this double bond oxygen, okay? With the LAH, you remove the double bond oxygen. So this is an example of a secondary amide would change to secondary amine. Basically, you're removing this double bond O. So if the acid derivative contains nitrogen, the reduced product is amine. For everything else is going to be primary alcohol. Nitrium contains nitrogen, so the final product is going to be amine. So you're getting actually primary amine. Other reactions of acid derivative with organometallic reagent. Example of organometallic reagent, we had alkyl lithium, we had Grignard reagent, and we had Gilman reagent, and we are going to look at some of those reactions with the organometallic compounds. So if you use 1 mole of this alkyl group with the organometallic compound, what is unique about is that the metal is positive and the carbon attached is going to be negative. So this alkyl group is going to use as a strong nucleophile, okay? So it's going to act as a strong nucleophile and is going to form bond with the carbonyl group. If you remember from previous chapter, I said anytime a nucleophile attacks a carbonyl group, you have to look, is there a leaving group or there is no leaving group? What happens if you have leaving group? The leaving group is going to leave. If there is no leaving group, then the pi bond will break over the oxygen. So in this case, for the first step, there is a leaving group. So you bring like an alkyl group, 1 alkyl group to replace with O etoxide. And then on the second step, because then you have like a ketone plus the alkyl lithium again, then nucleophile comes and forms bond with the CO double bond, and the pi bond will break over the oxygen. So final product is going to be a tertiary, because it's a formate. In this case, because it's a formate, it would give you secondary alcohol. So basically, two groups from the alkyl lithium, two alkyl group would replace or would add to the carbonyl. One of them would replace the alkoxide, and the other one will break the pi bond. So you end up with, in this case, you end up with secondary. Normally, you would end up with tertiary. Normally, if you don't have like the formate ester, so if you had like a CH3 here, it would have been tertiary. But since this is a formate, so you would get a secondary. For next reagent, when you have Grignard reaction, 2 moles of Grignard with acid chloride would also give you tertiary alcohol. The first mole, it will replace the Cl, and the second mole would break the pi bond over the oxygen, and you would protonate and you change that to OH. So you basically are adding 2 of the nucleophile part of the Grignard reagent. And the nucleophile part of the Grignard reagent is the alkyl group or the aryl group that makes the Grignard reagent. So based on the mechanism for Grignard, addition of Grignard to ester, the first molecule would give you ketone, and then the second molecule reacts with ketone and it gives you tertiary alcohol. Nitrile with Grignards, what happens with the nitriles and Grignard? The first molecule is going to change to, okay, the nucleophile, so you have a negative and positive, okay? Have a positive and negative charge here. So when the R group, which is the nucleophile from the Grignard, forms bond with this carbonyl group, the pi bond is going to break. So a pi bond is going to be, it's going to break, and it gives like a negative charge to the nitrogen, and you have this Mgx with the plus charge here, close to the negative charge, is going to be stabilized. So you are adding an R group on the first step. So you have the salt of the imine. When you hydrolyze this, it will change to CO double bond. Remember, if you have a CN double bond, you hydrolyze, it would give you CO double bond. And if you have CN triple bond, you hydrolyze it, it would give you COOH. So we have seen both of them today. So when you add Grignard, you're just adding 1 mole, and then you get the imine. With the imine, you hydrolyze it, you get to a ketone, or you would get to aldehyde functional group. Okay, so we learned about a lot of reactions, but since they are very similar, it's easy to follow because they're similar reactions. And you can summarize it based on one category or one acid derivative. Like if you talk about acid chloride, what are the different reactions? First of all, if you hydrolyze acid chloride, what would you get? Carboxylic acid, right? You hydrolyze acid chloride, you get carboxylic acid. And that is shown by the first reaction here. Hydrolysis of acid chloride would give you carboxylic acid. If you add alcohol to carboxylic acid, alcohol plus carboxylic acid would give you ester. Alcohol plus any acid derivative would give you ester. And then you get the byproduct. You add amine to acid chloride, you would get amide, and is a step up. If it's a primary amine, you would get secondary amide. If you add ammonia, you would get primary amide. And then acid chloride plus carboxylic acid, it would give you acid anhydride. So we looked at this reaction already. And this is just a summary of the reactions. So acid chloride plus 2 moles of Grignard would give you tertiary alcohol. Acid chloride plus a Gilman reagent would give you ketone. We learned that in chapter 18 as well. A Gilman reagent, R2CuLi, is known as the Gilman reagent, is milder than the Grignard. So only 1 mole of this is going to react and your final product is going to stay as ketone. But if you have Grignard, it will go all the way to tertiary alcohol. If you use poison LAH, it would stay at the aldehyde, 1-step reduction. If you use the LAH itself, it will go to primary alcohol. Other reactions of the acid chloride is like for acylation. You can use for the acylation with the benzene ring. You basically are adding acyl group, or you're making phenyl ketone. So you have to have the benzene ring here. So you're making like phenyl ketone. If there is a group already on the benzene ring, as we learned in chapter 17, that if it's an electron donor group, the new group is going to go to either ortho or para position. In this case, it's going to para position because you have a large group that is going to be replaced, and the choices of ortho and para is preferred. Reactions for anhydride. First of all, how do you synthesize anhydride? Is acid chloride plus carboxylic acid that will give you acid anhydride. Some reactions of acid anhydride is just like the trend. These are common reactions. You hydrolyze, it would get carboxylic acid. You add alcohol, it will give you ester. If you add amine, it would give you amide. So now if it's ammonia, it would give you primary amide. Primary amine would give you secondary amide, and the secondary amine would give you tertiary amide. You could also do Friedel-Crafts acylation using the acid anhydride, because acid anhydride, the benefit of acid anhydride is that it's going to provide you 2 acyl groups. So it's better to use the acid anhydride, but only 1 acyl group at the time is going to work. So if you have anhydride that is a cyclic anhydride, only one of them would react, would add to the benzene ring, and the other one would stay as the carboxylic acid. Acid anhydride plus alcohol would give you ester. Acid anhydride plus amine would give you amide. So very, very similar reactions. Reactions of ester, what type of reactions do you expect from esters? You hydrolyze, you would get carboxylic acid. You add alcohol to ester, you would get another ester, it's called trans-esterification. You add amine to alcohol, to ester, you get amide, and then you can reduce it. If you reduce it with LAH, it will go to primary alcohol. And you can add Grignard. If you add Grignard, it would give you tertiary alcohol. If you add Grignard, it would give you tertiary alcohol. Formation of lactones, your molecule must have both carboxylic acid and alcohol on the same carbon chain. And if you use a catalyst, like the acid catalyst, it can change to lactone, which is the cyclic ester. And if you want to make sure that this reaction shifts to the product side, it is best to remove the water. And we learned that in general chemistry based on Le Chatelet's principle. Amides. What can you do with the amides? Hydrolyze it, it would give you carboxylic acid. If you reduce it with LAH, because it contains nitrogen, it will change to amine. So if it's a primary, it would give you primary amine, secondary would give you secondary amine. So it doesn't change. If it contains nitrogen, it will change to amine. Okay. With the diphosphorus pentoxide, you can change the amide to nitrile. This is one of the rare reactions that can be just, is very specific. Amide changing to nitrile, you have to use this reagent of the diphosphorus pentoxide. And you can change that to primary amine by using, basically this reaction is a decarboxylation reaction. Okay, so you have to be careful if you're using this reagent rather than the LAH, because in LAH you are going to have all the carbons, and if you are using the bromine with the basic solution, you're going to lose the CO double bond altogether. Okay, just be careful of that part. Keep track of number of carbons, basically. If it's on the paper, it's not lose or gain money. It's just that you have to make sure you have enough number of carbon, or you maintain the number of carbon, the balance. So it can dehydrate, basically. The amide can be dehydrated to nitrile. When you dehydrate, 2 hydrogen from NH2 has to be primary, and oxygen from the CO double bond is removed. With the phosphorus oxychloride or a phosphorus pentoxide, or diphosphorus rather, with pentoxide. Formation of the lactones. Also, you need the carboxylic acid and amine functional group in the same carbon chain, and it's best if you have at least 3 carbon in between carbon from carbonyl or acid functional group and the nitrogen. So the cyclic system becomes either 5-member or 6-member. So this has to be 4 carbon or 5 carbon. Okay, summary reaction for nitriles. You hydrolyze nitrile, you would get carboxylic acid. You would use LAH. You are only, LAH reducing acid derivative. If there is a nitrogen, it would change to amines. And the nitrile would always go to primary amine. With 1 molecule of the Grignard, it can go to ketone after you hydrolyze. They will change to ketone with the nitriles. Okay.